Welcome back, everyone, to the Deep Dive. Today, we're going to be doing something a little different.
Yeah, this is a really interesting one.
It is. It is. So we're going to be looking at how the human brain, something that's, incredibly complex,
Mm-hmm.
is sort of providing unexpected inspiration for the future of AI.
Yeah,
Right? So, like, kind of a weird intersection there.
yeah, that's right.
We've got a research paper here called Neuroplasticity in Artificial Intelligence. An overview and inspirations on drop in and out.
Quite a mouthful.
Quite a mouthful, right? But it really does make some fascinating connections between the stuff that goes on inside our heads and what's happening in the world of artificial intelligence.
Yeah, and what I think is really interesting about this is it's not just looking at the basic idea of AI being modeled on neurons.
Right.
It's actually diving into this idea of the brain's ability to constantly change and adapt throughout our lives,
Right.
which is what we call neuroplasticity,
Yeah.
and how that can inform how we build artificial neural networks.
Yeah. And I think that's a really great point. We want to unpack this for you.
Mm-hmm.
Really explore these kind of intricate concepts, both from biology and from the AI side.
Yeah.
And sort of highlight these surprising parallels.
Yeah.
And really, I guess the mission today is to sort of show how AI researchers are increasingly looking to the brain. Not just for the initial spark, like, oh, the brain has neurons, maybe we can use that as a model, but for actually blueprints on how to make AI not just intelligent, but more flexible,
Yeah.
more efficient, capable of learning continuously,
Yeah.
right? And do it all without, getting too lost in the technical weeds, right?
Exactly. It's like this, our brains are always kind of adding these processing units.
Yeah.
And this paper is exploring how AI can benefit from being more dynamic rather than sort of having this fixed set of neurons from the start.
Yeah.
You know?
Yeah. Yeah. And it's important to remember that the very first ideas about artificial neural networks did actually come from our understanding of the brain.
Mm-hmm.
But, as the paper points out, a lot of the AI development since then has sort of focused on building these incredibly complex structures, these huge language models, right?
Right.
That we hear so much about, but, with sort of static foundations,
Yeah.
which is quite different from the brain's it's never-ending evolution.
Right. Exactly. Think about this. Your brain is never really set in stone.
Right.
It's constantly undergoing these fundamental biological processes.
Right.
And this paper really focuses on three key ones.
Okay.
First, there's neurogenesis,
Okay.
which is the creation of new neurons in the brain.
Right.
And then there's neuroapoptosis,
Okay.
which might sound a little bit alarming,
Yeah.
but it's essentially the programmed death of neurons. So
Okay.
it's like a natural process.
Right.
And then finally, there's this overarching term, neuroplasticity, which refers to the brain's ability to reorganize itself.
Right. So just to clarify, it's not just that neurons are being added. It's not just that neurons are dying off. It's that those things are happening, and also the brain is rewiring itself.
Exactly. It's
Okay.
like this constant state of flux.
Okay.
And what's remarkable is these aren't just things that happen when we're children, right?
Right.
Like neurogenesis, for example, continues in adult brains,
Wow.
particularly in the hippocampus, which is this area that's crucial for memory.
Right.
And studies suggest that around 700 new neurons are generated there every single day.
Wow.
So that's pretty amazing, right? Like we're constantly generating new brain cells.
Right. So our brains are constantly being replenished.
Yeah. And then on the other hand, you've got neuroapoptosis,
Right.
which acts like this kind of cleanup system,
Okay.
right? It eliminates neurons when they reach the end of their useful life
Right.
through these built-in self-destruct mechanisms.
Wow. It's really efficient.
It is.
So it's like a self-cleaning of it.
Yeah, exactly.
Right.
Keeps things running smoothly.
Wow. Okay. So we've got these two sort of opposing processes, I guess, happening at the same time.
Yeah.
And then this overall neuroplasticity sort of encompasses both.
Exactly. And it's not just about the coming and going of neurons. It's about how the brain rewires itself in response to what it experiences.
Okay.
So this includes things like synaptic plasticity, which is the way connections between neurons strengthen or weaken.
Right.
And then you have functional plasticity. So this is where if one part of your brain is damaged, another area might learn to take over its functions.
Wow.
Pretty amazing, right?
Yeah.
And then even structural changes like the growth of dendrites,
Right.
which help to form new connections between neurons.
So, I mean, think about it. Like when you learn a new skill, That's your neuroplasticity in action.
Exactly.
Right.
It's like your brain is constantly rewiring itself to accommodate new information and new experiences.
Wow. Okay, so this is happening all the time.
Yeah.
And it's essential, I guess.
It is. These processes are vital for us to adapt to environmental changes, to recover from brain injuries, and fundamentally to learn new things.
Okay.
And when you think about it, artificial neural networks are facing a somewhat similar challenge.
Okay.
They're constantly being presented with new data,
Right.
and there's a growing need for them to be able to restructure themselves in response.
So there's this kind of parallel then
Exactly.
between how the brain works and this challenge that AI is facing.
Mm-hmm.
Okay?
So that brings us to this really interesting point where AI researchers have already started looking to the brain for inspiration on how to tackle these challenges.
Okay.
And the paper highlights dropout as one existing technique in AI that actually has parallels with neuroapoptosis.
Okay. Now, for those of you who might not be, deep into AI,
Yeah.
dropout is it's this technique that's used when training neural networks.
Mm-hmm.
And essentially, it improves performance by randomly deactivating some neurons temporarily.
Yeah. And here's where this really interesting parallel emerges.
Okay.
Just like not every neuron in our brain is essential for every single task we perform.
Right.
Dropout in AI recognizes that not all artificial neurons are needed all the time.
Okay.
So by randomly deactivating some during the training process, it prevents the network from becoming too specialized to the training data,
Okay.
which is a problem known as overfitting.
Right.
Think about it like studying for a test by memorizing every single practice question.
Right.
You might ace that test, but you won't be able to answer anything that's slightly different,
Yeah.
right? So dropout helps prevent AI from doing the same thing with its training data.
Okay.
It encourages more robust and generalizable learning.
Okay. So dropout is kind of like AI's way of saying, let's not overthink this.
Exactly.
Yeah.
It's like, let's keep things flexible.
Okay.
Let's make sure we can generalize to new situations.
Got it. So dropout is sort of like an existing technique that's kind of mimicking neuroapoptosis in a way.
Exactly. It's like this artificial version of this natural process.
Okay. So then this is where the paper takes it to another level.
Yeah, this is where it gets really interesting.
Right. Because they introduced this new concept called drop-in, which they're proposing as the opposite of dropout.
Mm-hmm.
And it has a really striking similarity to neurogenesis in the brain.
Yeah,
Right.
that's right.
So instead of randomly deleting neurons, drop-in involves adding new neurons to existing artificial neural networks.
Yeah, so the thinking behind this is that just like the brain can potentially increase its capacity by generating new neurons,
Okay.
adding parameters, which in this case would be new artificial neurons, can potentially increase the learning capacity of AI models.
Okay.
And we've seen something similar with the impressive capabilities of large language models,
Right.
which often have a vast number of parameters.
Right.
So this raises a really important question. Could dynamically adding neurons be a key to even more powerful AI?
Yeah, that's fascinating. So I guess the question is, can AI benefit from sort of like a growing brain, so
Yeah.
to speak?
Exactly.
Right. Okay. So that's drop-in. That's
Yeah.
this new concept that they're proposing.
Yeah.
So just to kind of bring it all together, this paper, really has several objectives, I guess.
Yeah.
First of all, it aims to provide this overview of, neurogenesis, neuropoptosis, and neuroplasticity in both, the real world and in the world of deep learning,
Mm-hmm.
right? Second, it examines existing techniques like dropout. It introduces this concept of drop-in, and it looks at other similar approaches in AI. Then it takes a significant step further, I think, by suggesting actual algorithms
Mm-hmm.
for what they're calling artificial neuroplasticity.
Right.
And then finally, it opens up this discussion about the implications, the challenges, and the potential future directions for research at this, really interesting intersection
Yeah, it's like they're laying out this roadmap. Yeah.
for how we can start to incorporate these brain-inspired principles into AI.
Yeah, and I think it's worth considering, how this potential for AI to kind of move beyond these fixed architectures and embrace, more of a dynamic brain-inspired approach could really change how these systems learn and adapt.
Exactly.
Right.
Yeah. It makes you think about the future of AI
Yeah.
and how closely it might start to mirror that incredible adaptability we see in our own minds.
Right.
So let's dig into some of these key themes a little bit more.
Yeah.
So one of the things that the paper really emphasizes is this quest for finding the optimal neural network configuration.
Right.
Right.
Yeah.
Like, what is the best network structure
Right.
for solving a specific task?
Right.
And it's not just about making networks bigger and bigger, which is kind of this intuitive idea.
Right.
You know.
Well, I mean, there is this idea that, theoretically a neural network can approximate any function if it has enough capacity.
Right. But in the real world, it's always a balancing act.
Right. Right.
You have to weigh the cost of training against the model's ability.
Mm-hmm.
And you can run into all these problems like the AI becoming too specialized to its training data,
Mm-hmm.
or not being complex enough to learn properly.
Exactly. It's not a simple one-size-fits-all solution.
Right.
And this is where a really interesting parallel with the brain comes in.
Okay.
The paper mentions that the ideal number of parameters in an AI network, you can't calculate it precisely,
Right.
which mirrors this uncertainty we have in defining the exact number of neurons needed in the human brain.
Right.
We have general estimates, but we don't have a specific count.
Right.
So it's this kind of ongoing challenge of finding that right balance.
Yeah, it's this constant push and pull, isn't it?
Yeah.
We've seen this, in AI where often larger networks tend to achieve better performance.
Right.
Yeah. Think back to models like AlexNet, for example,
Mm-hmm.
as a significant early example.
Yeah.
And then more recently, the rapid progress in large language models has really underscored this point.
Right.
Right.
Bigger is often better, but not always.
Right. But at the same time, there's always been this counter trend
Right.
of pursuing smaller, more efficient networks
Mm-hmm.
that can achieve comparable results.
Yeah.
Right. Think of, models like SqueezeNet
Right.
or EfficientNet, right?
Yeah.
Where it's really about that efficiency.
Right.
And this leads us to the lottery ticket hypothesis, which is really fascinating.
Yeah.
This idea suggests that, within these massive randomly initialized neural networks,
Mm-hmm.
there's actually a smaller subnetwork
Right.
that has just the right initial settings,
Yeah.
that can be trained to perform just as well
Yeah.
as the entire much larger network.
Right. So it's like there's this winning ticket
Yeah.
hidden within this larger structure.
Right.
And it has the potential to be just as effective. But the challenge is finding it.
Yeah.
Right? Like, how do you identify and keep these best performing subnetworks?
Yeah.
It's like finding that perfectly efficient core
Right.
within a larger, perhaps less efficient system.
Right. So the lottery ticket hypothesis suggests that bigger isn't always better.
Exactly. Yeah.
Right. That there might be these smaller, more efficient networks hidden within.
Mm.
Okay. So and this is where the paper kind of connects back to this idea of neuroplasticity,
Mm-hmm.
right? Because it's saying that, not all parts of a neural network may be equally important,
Right.
right? And that kind of mirrors the brain's ability to, refine and optimize its connections.
Exactly.
Right. Okay. So then the paper kind of shifts its focus
Yeah.
to this really critical aspect of what happens when the task itself changes over time,
Mm-hmm.
or when the environment, around the AI evolves.
Right.
And this is where this concept of continuous learning becomes incredibly important.
Yeah. And this is where I think the brain-inspired principles can be really valuable.
Okay.
So in continuous learning, AI models need to adapt dynamically to new information,
Right.
changing conditions,
Right.
without forgetting what they've already learned,
Right.
which is a huge challenge known as catastrophic forgetting.
Right.
Like, imagine learning to ride a bike
Right.
and then suddenly forgetting how to walk.
Right. Yeah. Like unlearning a basic skill.
Yeah, that's kind of the AI equivalent.
Right. Yeah.
And it's a major hurdle in AI development.
Yeah. It's like you're constantly having to start from scratch.
Yeah, exactly.
Right.
So the paper talks about a number of approaches
Okay.
that try to tackle this.
Okay.
So things like online learning,
Right.
where models learn from data sequentially.
Okay.
And then there's transfer learning,
Right.
where knowledge gained from one task is applied to a new but related task.
Right.
Think about how you might use your knowledge of driving a car to learn how to drive a truck. Right, yeah. That's transfer learning in action.
Yeah. Okay, so that's transfer learning. Okay.
Yeah. And then there's reinforcement learning,
Right.
which is this kind of ongoing cycle of feedback
Right.
and adjustments.
Right.
So that's another way to approach continuous learning.
Okay. So, but the paper makes I think a really interesting point.
Yeah.
It says that most of these existing methods are primarily focused on dynamically adjusting the strength of the connections between neurons.
Yeah.
But the structure of the neural network, like the fundamental structure,
Mm-hmm.
tends to stay largely unchanged.
Right.
Right.
Yeah.
And this is where the inspiration from neuroplasticity, with this ability to actually add and remove neurons, could be a game changer.
Exactly.
Right.
Yeah.
So the paper proposes that by allowing the architecture of the network to change over time,
Mm-hmm.
AI could potentially overcome some of the limitations that we see in these current continuous learning methods.
Right. It's like, imagine if your brain couldn't grow new neurons.
Right.
Right. Or couldn't prune away unnecessary connections.
Yeah.
It would severely limit your ability to learn and adapt.
Right.
And that's kind of the situation AI is in right now.
Okay, so they're suggesting that we really need to look to this neuroplasticity for inspiration
Yeah.
in making AI better at this continuous learning thing.
Mm-hmm.
Okay.
Yeah.
So let's delve a little deeper into, how the paper specifically links these biological concepts to AI.
Yeah.
So it points out, how other researchers are already drawing these parallels
Mm-hmm.
between the physical structures of neurons in the brain
Right.
and elements in AI, even suggesting that the weights of connections in a neural network
Mm-hmm.
could be seen as similar to the efficiency of synaptic connections in our brains.
Right.
Right. The stronger the connection,
Yeah.
the more influence one neuron has on another.
Exactly.
Right? And this idea of environmental enrichment, from neuroscience,
Mm-hmm.
where stimulating environments can lead to enhanced brain function,
Right.
is also being explored in AI,
Mm-hmm.
right? With the suggestion that techniques like transfer learning, right, could play a similar role
Yeah.
in boosting the capabilities of artificial neural networks,
Yeah.
right, by exposing them to a wider range of information.
Exactly.
Okay, so that's kind of, interesting.
Yeah.
But the paper really takes this a step further.
Mm-hmm.
By breaking down neuroplasticity in AI,
Mm-hmm.
right,
Yeah.
into these two key components,
Right.
right, neurogenesis,
Yeah.
which they're connecting to this idea of drop-in,
Mm-hmm.
right, the addition of neurons,
Yes.
and then neuroapoptosis,
Mm-hmm.
which they're linking to these existing techniques like dropout and structural pruning,
Right.
right, so the removal or deactivation of neurons.
Right.
Okay, so let's look at these in a bit more detail. Let's start with drop-in. So as we've discussed, drop-in is proposed as this conceptual opposite of dropout,
Mm-hmm.
right?
Yeah.
Directly inspired by neurogenesis.
Right.
And the paper defines it as a technique that randomly activates additional neurons and connections during the training of an AI.
Yeah.
So the core idea is that this could increase the network's ability to learn, right?
Yeah.
More intricate patterns,
Yeah.
develop more robust, sort of ways of understanding information
Mm.
by dynamically adapting to this increased complexity.
Exactly.
Right. And the paper even suggests specific situations where drop-in might be particularly useful,
Mm-hmm.
right? Such as when there's a significant change in the environment that the AI is operating in,
Right.
right? Maybe new types of tasks.
Yeah.
Or a sudden influx of new data,
Mm-hmm.
or if the network seems to have reached a limit in its performance,
Right.
right? So it's like drop-in could be a way to kind of push the AI beyond its current capabilities.
Mm-hmm. Exactly. It's like giving it a boost.
Right.
When it needs it most.
Yeah.
Yeah.
Okay. And then, so they propose this algorithm for drop-in, right?
Yeah. This is where they get into the specifics of how it might work.
Yeah. Yeah. And it involves, monitoring how well the AI model is performing,
Mm-hmm.
right?
Yeah.
Essentially, how accurate are its predictions?
Right.
And if the performance stops improving significantly,
Mm-hmm.
right, suggesting that maybe the network's kind of reached its current capacity,
Yeah.
the algorithm could then randomly select and add new neurons and the connections between them.
Right.
Right. And the paper suggests that, this change would kind of influence two consecutive layers,
Mm-hmm.
right, within the neural network.
Yeah.
And this process would continue,
Mm-hmm.
right, as long as the model's performance on a separate validation data set
Right.
keeps improving.
Yeah.
But then, during the actual use of the AI, after training,
Mm-hmm.
all the neurons would be active.
Right. So it's like during training, it's experimenting
Right.
with adding new neurons
Yeah.
to see if it helps.
Right.
But once it's deployed, it uses all of its available resources.
Yeah. Okay, so that's their drop-in algorithm.
Uh-huh.
Now, they acknowledge that drop-in, as they've described it, might not, be explicitly present in current AI research.
Yeah, that's true.
Right.
But they point to some related ideas,
Okay.
like model expansion,
Right.
where the overall architecture of a neural network is enlarged
Right.
to handle new tasks.
Right.
or to address situations where the model isn't complex enough to learn from the data.
Right.
So we've seen examples of this, like with large language models being extended with new data,
Mm-hmm.
or smaller models having entire layers added or expanded for specific tasks.
Right.
And they also mention adaptive learning,
Right.
especially in the context of fine-tuning,
Right.
and further training large language models using techniques like adapters, which are efficient ways to modify these massive models
Right.
without retraining everything from scratch.
Right. But the key distinction that the paper makes
Yeah.
is that these existing methods often operate at the level of entire layers, right,
Right.
within the network.
Yeah.
Whereas their drop-in concept
Yeah.
is more about working at the level of individual neurons,
Right.
right?
Yeah.
Which more closely mirrors neurogenesis in the brain.
Exactly. It's like a more fine-grained approach
Yeah.
to adapting the network.
Yeah, yeah. Okay, so that's drop-in. Now let's shift our focus to neuroapoptosis in AI.
Yeah.
And this is where the paper highlights these existing methods like dropout and structural pruning as sort of analogous processes.
Right.
Where connections are either temporarily deactivated or entire neurons are permanently removed.
Yeah.
So we've already talked about dropout a bit
Mm-hmm.
as this technique used to prevent AI from becoming too specialized to its training data
Right. Yeah.
by randomly setting a portion of neurons to 0 during training.
Yeah, it's like temporarily silencing them.
Right.
To prevent them from having too much influence.
Okay. So the paper provides a pretty good overview of how standard dropout works, right? But then it also delves into all these different ways
Yeah.
that researchers have kind of refined this basic idea.
Yeah. This is where it gets really interesting. It's like they've taken this core concept
Yeah.
and they've come up with all these clever variations
Right.
to make it even more effective.
Okay.
So you have things like efficient dropout methods
Right.
that use mathematical distributions to speed up the process.
Okay.
And then there are adaptive dropout techniques
Right.
that dynamically adjust the proportion of neurons being dropped out
Okay.
during training
Right.
based on how the model is performing.
Okay.
And then you even have trainable dropout,
Wow.
where the parameters controlling the dropout are themselves learned by the AI.
So it's like the AI is figuring out the best way to drop out.
Right.
Right.
Okay, so that's really interesting.
Yeah.
And then there are these model-specific dropout strategies that are designed for, specific types of neural network architectures,
Right.
like, spatial dropout,
Yeah.
which is used in convolutional neural networks that process images,
Right.
or RNN dropout, which is used in recurrent neural networks
Yeah.
that process sequences of data.
Right, like text or time series.
Right, right.
So it really shows how this fundamental concept of randomly deactivating neurons has been adapted
Right.
and refined in all these clever ways to enhance the learning process.
Yeah. So it's like dropout is this really versatile tool.
Exactly.
Right?
Right.
That can be adapted and customized to suit different needs.
Right.
Okay. So then we've got structural pruning, which kind of takes this idea of neuroapoptosis, I guess, a step further.
Yep.
Right. Because unlike dropout, which is a temporary deactivation, structural pruning involves permanently removing neurons
Right.
or connections between them
Yeah.
that are deemed to be not really contributing to the AI's performance anymore.
Yeah, it's like getting rid of the dead weight.
Right.
So it can make the network more efficient.
Right. And the paper explains that pruning can happen at different levels. You can prune individual connections.
Right.
You can prune entire neurons.